All right, we're going to go ahead and take a look at section 1-4, which deals with combinations of functions. Specifically, it's going to deal with composite functions. So we're going to go ahead and define what a composite function is to start with. So given two functions, f and g, the composite function denoted by, so you'll see f and then an open dot and then the function g. Okay, and the way that you read that, that's read as f composed with g is defined by this equation. So if we have f composed with g of x, that is equivalent to the composition f of g of x. Okay, so the function that's listed second is the inner function in the composition, and the function that is listed first is the outer function in the composition. Okay, so we're going to do some things with these composite functions. We're going to spend some time like evaluating composite functions. We're going to spend a lot of time looking at the domain of composite functions as well. Okay, so first set of examples is going to ask us to evaluate composite functions. So directions say to suppose that the function f of x is x squared plus 4x, and g of x is equal to 5x plus 1. Then part A asks us to find f composed with g of 1, and part B asks us to find g composed with g of negative 2. Okay, so for part A, if we want to find f composed with g of 1, that is like asking us to find f of g of 1. So the first thing that we want to calculate is we want to calculate the inner value in the composition. Okay, so we want to calculate g's value at 1 first. So when we plug 1 in the place of x in the function g, we get 5 times 1 plus 1, which is 5 plus 1, which is going to make g of 1 equal to 6. So when we're being asked to find f composed with g of 1, essentially that is asking us to find f of 6, because we're just plugging 6 in wherever we see g of 1. Okay, so if we want to calculate f's value at 6, we plug 6 in the place of x in the function f, so that's going to be 6 squared, which is 36, plus 4 times 6, which is 24, and 36 plus 24 add up to 60. Okay, so f composed with g of 1 is going to be equal to 60. Okay, for part B, g composed with g of negative 2, that's asking us to find g of negative 2. So again, we're going to evaluate the inner function in the composition first, so g of negative 2. So when we plug negative 2 in the place of x for our function g, we get 5 times negative 2, which is negative 10, plus 1, which that simplifies to negative 9. And then we're going to plug negative 9 in the place of g of negative 2. So that composition essentially becomes g of negative 9. So when we plug negative 9 in the place of x in our function g, we get 5 times negative 9, which is negative 45, plus 1. So that composition is going to be equal to negative 44. Okay, so that's pretty straightforward, pretty simple. The bulk of the rest of the lesson is going to deal with us finding domains of composite functions. All right, so next example says to suppose that f of x is equal to x squared plus 2x minus 5, and g of x is equal to 3x minus 2. And then we're asked to find f composed with g and state its domain. Okay, so when we're asked to find f composed with g, essentially that is asking us to find f of g of x. And since g of x is equal to 3x minus 2, that's asking us to find f of 3x minus 2, which means I'm going to plug 3x minus 2 in wherever I see an x in the function f. All right, so that's going to give me 3x minus 2 squared plus 2 times 3x minus 2 minus 5. And then we just want to expand that result out. So 3x minus 2 quantity squared, when I FOIL that out, that's going to become 9x squared minus 12x plus 4. When I distribute 2 across the next binomial, we get plus 6x minus 4. And then we have our constant term minus 5. Okay, so last thing for me to do here is to combine like terms. So 9x squared, that's my only squared term. We have negative 12x plus 6x, which simplifies to negative 6x. And then we have plus 4 minus 4. So 4 and negative 4 cancel, which leaves us with the constant of negative 5. Okay, now I am willing to guess that when teachers at Oxford teach finding domains of composite functions, they're probably going to do it in a different manner than I do. There are a couple different ways for you to interpret it, but I find that this is the easiest way for you guys to do so. Okay, so when we find the domain of a composite function, first domain we always want to calculate is the domain of the inner function in the composition. Okay, so the inner function in the composition is the function g. G is a linear function, which makes it a polynomial function, and the domain of any polynomial function is all real numbers. And I don't care if you write it right now in set notation or interval notation. I'm going to do set notation for this. Okay, so we calculate the domain of the inner function first. Next domain we calculate is the domain of the composite function, f composed with g, which is this function here that we just found. So again, f composed with g is a quadratic function, thereby making it a polynomial function. And the domain of a polynomial function, again, is going to be all real numbers. Okay, so if we want our domain, the domain is just going to be the overlap of the two domains that we just found. So when I say overlap, I mean like what values those two sets or intervals have in common. Or another way to think of overlap is like the more restrictive of those two domains that we calculated. Okay, so what values do those two, in this case, sets have in common? It's the set of all real numbers. So it's a set of x such that x is a real number. Okay, so that's the domain of your composite function. And this right here is the composite function itself. Okay, and like I said, I think that's the easiest way for you guys to determine the domain of a composite function going forward. All right, so let's try another one. So directions for the next one ask us to find the domain of f composed with g of x if f of x is equal to 3 over x minus 1 and g of x is equal to 2 divided by x. Okay, so f composed with g of x is like asking us to find f of g of x, which is f of 2 over x, which means I'm going to plug in 2 over x wherever I see an x in the function f. So when I do that, we get 3 over 2 over x minus 1. Now, this is what we call a complex rational expression, where we have like a smaller fraction, which in this case is 2 over x, that's a part of the larger fraction, which is 3 over 2 over x minus 1. So I feel that the easiest way to simplify a complex rational expression is you want to determine what the common denominator is going to be for your smaller denominator, okay, which in this case is x. And the common denominator there is just going to be x. So we're going to multiply the numerator and denominator by x. All right, so when I multiply across, the numerator 3 times x makes 3x. When I multiply across on bottom, 2 over x times x makes that first term on bottom 2, minus 1 times x makes the next term negative x. Okay, and now that composite function there is simplified completely. Okay, so if I want to calculate domain, the first domain we're going to calculate is the domain of the inner function g. Again, I'm going to write this in set notation. I think it's going to be maybe a little bit faster. Okay, so the domain of the inner function g, the function g is rational. We know our denominator cannot be 0. So it's going to be the set of x such that x can't be equal to 0. Next domain we calculate is the domain of the composite function. And the composite function here is also rational. So once again, our denominator cannot be equal to 0. So the value that makes our denominator 0 is 2. So we know x can't be equal to 2. And if we want to calculate our domain is the overlap of those two sets. So what values can x not be equal to? We know that x can't be equal to 0, and x can't be equal to 2. All right, so that right there is the domain of that composite function. Okay, go ahead and get this next one copied. I want you guys to work on this one. So you're going to pause the video, give this one a try. So again, directions here say to suppose f of x is equal to x over x minus 1, and g of x is equal to negative 4 over x. And then you're asked to find in part A, f composed with g. In part B, g composed with f. And in part C, you're asked to find the domain of each composition. Okay, so I want you to pause the video, give those a try, and then we'll take a look at those together. Okay, so let's see how we did with this. So part A, f composed with g, that is f of g of x, which is going to be f of, we're going to rewrite g of x as negative 4 over x. And then if we want to find that composition, we're going to plug negative 4 over x in the place of x in the function f. So we get negative 4 over x over negative 4 over x minus 1. Again, if I want to simplify this complex rational expression, I'm going to look at the smaller denominators and determine what the common denominator of those smaller denominators is, which in this case is going to be x. So I'm going to multiply the top and bottom by x. And when we do so, when I multiply on top, negative 4 over x times x is negative 4. On bottom, negative 4 over x times x is negative 4. Negative 1 times x is negative x. And you can leave things in that form. That's fine. But I see that like I can factor a negative out of both the numerator and denominator. So I can write that fraction like this. And then I can cancel the negative factors on top and on bottom. So that's going to become 4 over 4 plus x. I prefer writing it in this manner. Okay, so that's that first composition. Then we want to calculate the domain. So if we want to calculate the domain, first domain we calculate is the domain of the inner function g, which g is rational. We know that our denominator can't be 0. So it's going to be the set of x such that x can't be equal to 0. Next domain we calculate is the domain of the composition, f composed with g, which again is also a rational function. We know our denominator can't be 0, so that's going to be the set of x such that x can't be equal to negative 4. And then our domain is just going to be the overlap of those two. So it's a set of x such that x can't be equal to -4 or 0. All right, so that's pretty straightforward. Okay, for part B, we want to calculate g composed with f. So that is g of f of x, which is going to be g of f of x is x over x minus 1, which means we're going to plug x over x minus 1 wherever we see an x in the function g. So that's going to be -4 divided by x over x minus 1. Again, we have a complex rational expression. To simplify this, I want to multiply the numerator and denominator by the common denominator of the smaller fraction, okay, which in this case is x minus 1. So when I multiply across, we get -4 times x minus 1. And then on bottom, when I take x over x minus 1 and multiply it by x minus 1, the x minus 1's cancel, which leave us with x. Okay, so that right there is our composite function. Okay, if we want to calculate domain, first domain we determine is the domain of the inner function, which is f. Again, that function is rational, so our denominator can't be 0, which means that x can't be equal to 1. Next domain we calculate is the domain of the composition g composed with f, which is also rational. Our denominator can't be 0, so it's going to be the set of x such that x cannot be 0. So our domain is the overlap of those two sets, which is the set of x such that x can't be 0 or 1. Okay, on to the next one. So directions here say if f of x is equal to 2x minus 6 and g of x is equal to 1/2 the quantity x plus 6, we want to show that f composed with g of x is equal to g composed with f of x. And we want to show that both of those compositions are equal to x for all x. Okay, so let's do f composed with g first. So f composed with g of x is going to be f of 1/2 the quantity x plus 6, which means I'm going to plug 1/2 the quantity x plus 6 in wherever I see an x in the function f. So that's going to be 2 times 1/2 the quantity x plus 6 minus 6. I can go ahead, I mean, there's a couple of different ways that you can simplify. I think probably the fastest way is just to multiply 2 times 1/2, and those are going to cancel one another out, and we get x plus 6 minus 6. So we show that that first composition there is equal to x. Okay, next composition, g composed with f of x, is g of f of x, which is 2x minus 6. So when I plug 2x minus 6 wherever I see an x in the function g, we get 1/2 times 2x minus 6 plus 6. When we simplify what's inside the parentheses, the 6's cancel. So we get 1/2 of 2x, which that composition is equal to x as well. The significance of that we're going to talk about in the next section. But what we did in this example here is we showed that f of x and g of x are inverse functions. Okay, so that's going to be an important idea for us in the next lesson. So that's one of the things that we're going to take a look at in the next lesson, like how do we algebraically show that two functions are inverses? And that's how we do it. We show that the composition of those two functions each way, both of those compositions are equal to x. Okay, so that'll end this video. We'll pick up the next video working through some additional examples.